We're taking a look at section 3.3 today, and before we get started, we want to take a look at this warm-up, which comes out of section 3.2 and covers some of the main points. Given the differential equation, says 2t squared y double prime plus 3t y prime minus y equals 0. Find the longest interval that contains the point 1, 1 in which the solution is certain to exist. So if you haven't already done this warm-up, then give it a try for a second. And then let's take a look at the solution. So in section 3.2, we came up against a wonderful existence and uniqueness theorem for second order linear differential equations. And what we're going to do is kind of start by putting it in this kind of canonical form where we make the coefficient on y double prime 1. And then we have these kind of coefficient functions on y prime and on y. And the requirement is for this theorem from section 3.2 that those be continuous. Of course, the issue is when t is 0. It says find the longest interval that contains the point 1, 1. So that's, the first coordinate is our t coordinate, t equals 1. And so we just need an interval that contains 1, and we want to make it as big as possible, and we want to avoid 0. And so, of course, that answer is 0 to infinity for part A. For part B, it says show that these two functions form a fundamental set of solutions on this interval. So, okay, well, first, this is kind of asking two things. First of all, we need to verify that these are solutions at all, and that's kind of a first day of differential equations task. So let's go ahead and, it's a straightforward task, but let's go ahead and verify that these are in fact solutions at all. First, starting with y1, we'll take t to the 1/2 and take its first and second derivative. And now we'll plug those into the original differential equation and see that we in fact do get, after simplifying, 0. And now let's do that again with y2 equals t to the negative 1. Take the first and second derivative, plug those in to our original differential equation on the left side, and sure enough, we get 0 as well. So those do, in fact, constitute solutions to the differential equation. But a concern that we always kind of have lurking in the back of our minds in this course is, yes, maybe those are solutions, but do we have them all? That is, another way of asking that is the general solution to this differential equation y equals c1 times t to the 1/2 plus c2 times t to the negative 1? Or could there be some other solution that isn't entailed by that? That would be the worry that we have. But we have this guarantee from this theorem in section 3.2 that if the Wronskian is not 0, then this does in fact form a fundamental set of solutions. So let's take a look at the Wronskian. Remember, it's this matrix determinant where we have in the first row loaded in the two functions, and in the second row we've loaded in their derivatives. Now we compute the determinant. Here we get -3/2 times t to the -3/2. And for our interval, that is never 0. So therefore, these do in fact form a fundamental set of solutions on the interval. So that's a nice summary from our learning in section 3.2. And now we're ready to jump into section 3.3. These two solutions form a fundamental set of solutions, we said. We're also going to now use in this section the term, we're going to say these two functions are linearly independent. So that's what we're going to learn in today's lessons. We're going to look at the linear independence of solutions, how that connects to the Wronskian, and in particular, we're also going to learn how to compute the Wronskian without even having the two solutions. Now that sounds like something to look forward to. So let's get into this. Before we go too far, we should review what we mean by linear independence or dependence. The context in which we might be most familiar with that is from our multivariable calculus studies and with the context of vectors. Let's take a look at these three vectors and ask ourselves, are these linearly independent? So take a second, I don't know, maybe you can remember how you might approach this. There are a couple different ways to approach it, but what do you remember? Okay, if you had a chance to think about it. Oh, if these were two-dimensional vectors, it would be maybe pretty quick and clear, because if two-dimensional vectors are linearly dependent on each other, then they're just scalar multiples of each other, and that's kind of easy to see, just maybe by inspection. That's why I gave you three-dimensional ones, just to make it a little more of a challenge. It's not so obvious whether they're dependent or independent when you're looking at three-dimensional vectors. But one thing you might remember that's starting maybe to come back to mind is this notion that three vectors define a parallelepiped in three-dimensional space. Remember, that's the three-dimensional analog of a parallelogram in 2 dimensions. So what does that have to do with this? Well, if we could compute the volume of the parallelepiped that's defined by these three vectors, then we might be interested to know whether that volume is 0 or not. Because if it's 0, then the vectors lie in the same plane, and that means that one vector can be expressed in terms of the other two, which is what we mean by linear dependence. So let's see if we can do that. Can we remember how we calculate the volume of the parallelepiped defined by these three vectors? The way we do it, and we can go back into all the theory if you like, but let's just assume you do remember how to do this. You use the scalar triple product to do that. You load in all three vectors and take this determinant, and this is going to give us the volume of that parallelepiped. So let's see what we get, which is kind of a straightforward computation. Let's do this matrix determinant. I'm just going to expand across the top row. We get 3 times 18, I guess, minus 14 minus 40, so that's 54 minus 14 minus 40, which is 0. Okay, so this is one of those cases where these three vectors are apparently linearly dependent. Okay, so I guess we answered the question, but maybe that's still not very satisfying to you. You might wonder, okay, so there's this dependency. What is the dependency? Well, by linearly dependent, we mean, recall that what we mean by that is that C1, there's some constants, C1, C2, and C3, such that C1 times vector A plus C2 times vector B plus C3 times vector C is equal to 0. And for some non-zero values of those, of course, right? And so how do we find those? Well, keep in mind that the thing we're looking at, although it looks very compact in its notation, is really that's C1 times A, that's a vector A of constants. So really the only thing to solve for here are these three constants, C1, C2, and C3. And really we're not looking at one equation. We're really looking at a system of 3 equations if you load those vectors in. 3 equations and 3 unknowns. So really we have a system to solve, and you could solve that in whatever way you like, maybe by row reduction. And when you do, I'll just skip the details, you'll get that C1, C2, and C3 are 2, -3, and -1. And so that gives us that relationship between A, B, and C that we were kind of promised. There is that dependency. And you might express it that way, or you could write, just to make it really clear that like one vector can be written in terms of the others, we can write C, for example, as a linear combination of A and B. And you can see that it's just like C is just 2A minus 3B. This is nicely pictured by these pictures on the left and right here. On the right is the picture of what we're dealing with right now, where we have C, A, B, and C are coplanar, and C can be written in terms of A and B. In the left diagram, I'm a little troubled by the fact that C is perpendicular. That wouldn't have to be true, right? C could be just anything that is not coplanar with A and B. And that would be the other situation where A, B, and C are, in fact, linearly independent. For functions, the situation is much the same. It's really the same thing. If two functions, let's say y1 and y2, are linearly dependent, then the same relationship holds, that there's some linear combination of them with non-zero constants, C1 and C2, let's say, that equals 0. Let's try this with a few functions. Give it a second here and take a look at each of these and see if you can figure out whether these are linearly dependent or independent. You can do them pretty easily by inspection. So for the first one, you can pick any number of different constants that'll work here. How about, I'm just picking 2 that work. How about 6 and -3? Obviously you could use 2 and -1 or any scalar multiples of these numbers in blue. Therefore, these are dependent. How about the next one in B? Okay, well, if you said that they were independent, I think your hunch is good. You can see that no matter what C1 and C2 are, provided they're non-zero constants, there's nothing that's going to make that happen to make those 0 for every number. So those are independent. Now the next one, I'm trying to be tricky here, but if you know your trig, then you know that the cosine of t minus pi over 2 is just like the cosine function moved right by 90 degrees, and that's just the sine function. And so those are the same, really. They're the exact same function, y1 and y2. So how about the constants 1 and -1? That'll give us the dependence that we need. And then what about the last one? Those two functions are linearly independent because, again, there's nothing that C1 and C2 can be, except for 0, that would make that linear combination come out to be 0. So those are independent. And you can see that what I mean by independence is really just the definition of dependence, but like not that, right? So if there's no such constants, then we just declare them to be independent. So now let's present the theorem that maybe ties some of this stuff together, this idea of linear independence and the Wronskian, which we promised we'd make a connection between these. So let's read this theorem. It's really just exactly word for word from our book, but let's try and unpack it with a few examples here. If f and g are differentiable functions on an open interval I, and if the Wronskian is not 0 for some point, for even one point in the interval I, then f and g are linearly independent on I. That is, so let's pause and think about that first sentence of this theorem. That is, if f and g are have a Wronskian that's not 0 for even one point, then it's linearly independent on the whole interval. All we have to do is check one point. Interesting. Okay, that's interesting. Let's ask this. Let's look at the second part here. Moreover, if f and g are linearly dependent on I, then the Wronskian will be 0 for every x in I. All right, let's take a look at two different sets of functions. In the first case, we've got the Wronskian, e to the 3x and e to the 3x minus 3. Let's set it up in our Wronskian. I've got the derivatives there using a little bit of the chain rule. And now as we go do the first diagonal, we get 3 e to the 6x minus 3, obeying our rules of exponents. And on the second diagonal, we get the same thing, and as we subtract, we get 0. Therefore, these are, well, this is the case where we have the Wronskian being 0 for every value. We didn't specify an interval, but it could be the whole real line, right? And so therefore, these two functions are linearly dependent. I think maybe you already knew that, though. Again, I'm trying to be tricky here, but there's only so much I can do. Now, the next one, again, I think you have a hunch that these are linearly independent, right? Let's check this with the Wronskian. It's trying to tie these concepts together. Sorry. So for those, the Wronskian is this, of course, and as we compute that, we get x to the 4th. Okay, well, that's interesting, x to the 4th. So what can we conclude there? This is interesting. Is that 0? Well, there is actually a moment when it's 0, if x happens to be 0. But if we're talking about, let's say we want to talk about the interval being, again, the entire real number line. That actually will work here, because if the Wronskian is non-zero for even one place, let's say x equals 1 or something, doesn't matter, pick one, then we're going to be able to say from our theorem that these two functions are linearly independent on the entire real number line. The fact that there might be one place where it's 0, let's say, like this one has, doesn't affect the result of that theorem. These are linearly independent functions, which is, I think, just confirming what we already knew. All right, now we're going to find the Wronskian without even knowing the two solutions. This is what we promised at the beginning of our lecture here today. And we're going to work it through, kind of figure it out ourselves without the theorem, and then we'll present the theorem on the next slide. So suppose we do have the solutions y1 and y2. We're going to first suppose that we have them and then realize that we don't need them in a minute. If that's really true, that y1 and y2 satisfy the differential equation, then we can plug them in and their derivatives, and those two statements should be true. And now we're going to do a little bit of algebra. Let's multiply the first equation by negative y2 and the second equation by y1. And now we're going to add them. When we do that, notice especially the third term. The third term will be in the two equations, q of t times y1 times y2. In the first equation, it'll be negative, and in the second equation, it'll be positive. And so when we add those are going to eliminate. The rest of the equations, though, are not going to eliminate. And so what do we get there? Well, verify that I've done this correctly. Did I collect terms correctly? You'll also see what I did is I collected the terms that have a p of t and the terms that don't. And now notice my color coding. Do you notice anything special about the green? Yeah, that kind of looks like a determinant, doesn't it? It's the, oh, there it is, you guys. The green maybe gives it away. I put the word Wronskian up at the top in green. It's the Wronskian, you guys. Yeah, isn't it? I mean, think about what the Wronskian is. And isn't it y1, y2? And then in the second row, y1 prime, y2 prime in the second row. And there's the determinant of that, right? Now the purple is a little harder to see. But the purple is also something special. It's in fact the derivative of the Wronskian. Now you're going to need to double check that off to the side on some paper, but you're going to see something nice that happens though when you do it. Try taking the derivative of the green Wronskian. When you do, you're going to need to take two product rules, right? And you're going to see that two terms completely cancel out. I promise. Go ahead and check it. I promise you'll get the thing we have in purple. That's great. So, okay, let's just summarize what we just did, I guess. So I guess what we're looking at is like w prime plus p of t times w equals 0, or if you like Leibniz notation, there you go. And, well, that's interesting. We've got a differential equation that's not like in terms of y, but in terms of in terms of like the Wronskian function w. Well, that is actually its own little, very nice differential equation. Let's take a look at that. Isn't that cool? We can easily solve that. It's separable. I won't bore you with the details. There it is. We've done it. We've found the Wronskian without actually even needing y1 and y2. The Wronskian is equal to c times e to the negative integral p of t dt. Yay. And now on the next slide, we'll summarize this in its formal theorem, but we've kind of already figured it out. This theorem is called Abel's theorem. So here it is in all of its glory. Take a second to read this with me and make sure it says what we just discovered that it kind of should say on the last slide. We got y1 and y2 are solutions to the homogeneous second order linear differential equation, where p and q are continuous on the open interval I. Then the Wronskian is given by that formula that we just derived. There it is, where c is some constant that depends on y1 and y2, but not on t. The Wronskian is 0 for all t and I if c is 0, or if it's never 0 if in I if c is not 0. Notice that as well. There's Abel himself. All right, so let's now do this with the warm-up problem that we started with. Could we, even if we didn't know those two solutions that I provided, could we still find the Wronskian? Sure, let's proceed. The first thing we're going to need to do is, again, put it in that canonical form so we know exactly what p of t is. Now, the one thing that's kind of interesting about this is we're about to use Abel's formula, the one we all developed together just a minute ago. But did you notice that we don't need anything except for that p of t function? So there it is. It's kind of fun. That's all we need. And so we're going to run that through. It's c e to the negative integral of p of t dt. So I'll assume that you can land that. We get c t to the negative 3/2. Now, isn't that interesting? Isn't that what we saw in the warm-up? Go back and look. And of course, we're going to get some constant there because the fundamental solutions that we have, remember, it was the two solutions we had were t to the negative 1/2 and t to the negative 1, I think, right? But remember, someone could have easily given us some constant times those as well. And so that c is kind of still up for grabs. It's going to be some constant times that, though, right? If we had done that in the warm-up and we would put constants on those, we would have gotten a different Wronskian. Well, it wouldn't really have been different at all. It would have been this, would have been something times t to the negative 3/2. So we can draw this conclusion that whatever y1 and y2 are, they will form a fundamental set of solutions there. Now, I know that doesn't seem very satisfying. It seems like, well, that doesn't seem like what we need here. We really would like to find those solutions, but I promise in the coming lessons we're going to find some really important uses for the Wronskian, even though you know, well, I'll just tell you right now, one thing we're going to be able to do is we're going to be able to, if we have one solution, we're going to be able to find the other using the Wronskian. So that's going to be in particular, one nice application. So let's summarize our lesson. Again, I've stolen this from the book, but this is a nice little summary of the theorems from this section a little bit. So if y1 and y2 are solutions to our canonical differential equation here, it's a second order linear homogeneous equation, where again p and q are continuous on an open interval I, then these are all equivalent statements. So for number 1 and 2, I think we have that set in our minds probably, right? If we have two solutions that are a fundamental set of solutions, then that means the same thing as linearly independent. So if you say they're linearly independent, there's interchangeable terms. I can say, oh, you mean a fundamental set? Point number 3 there says that, remember, if the Wronskian is not 0 for even 1 point, then they're going to be linearly independent or a fundamental set of solutions. So that connects back up to point number 1 and 2. And then for point number 4, if the Wronskian is not 0 for all t in the interval, then we have a fundamental set of solutions. Now this one, I had to think about this hard as well, because this does seem to say something a little bit different than we said earlier. This last point, you might be thinking, well, wait, I thought that it could be that the Wronskian is 0 at certain points. But this is a very particular situation. If it's in this particular canonical form that I have up here, then this is going to be the case, that the Wronskian is never going to be, if it's not 0 somewhere, it's not going to be 0 at every place in the interval. It's a little bit of a nuanced point, but so yeah, I don't know if I want to get it. It's not like the most important thing for us right now. But for example, if we go back to x squared and x cubed, I said that, or let's use t here because that's what this says. If we had like the solutions t squared and t cubed, which we used on a couple slides ago, you might think, well, those are linearly independent, but they're 0 at 0. But I'll just tell you right now that those can't be solutions to an equation of this form right here. They could be solutions to an equation where we have a coefficient in front of the y double prime, like that has a t in it. But then when we divide through, 0 will be a singularity, will be a place where it's undefined. And so then it'll go back to that existence and uniqueness thing, and we won't even be able to have unique solutions that contain 0. And so then everything's okay. So that's a really, oh man, I hate to kind of throw that really fine nitpicking point in at the end, but I wouldn't worry about it too much for now. Just know that look at the big brush strokes on this. And if I'm happy to answer some more questions about that point number 4. It's kind of a sticky one. All right. Well, I hope that even with that a little unsettling ending there, that we've had a good discussion of section 3.3. Here are the extra resources. You can take a look at those resources for even more greater depth on this lesson. Thanks you guys for listening and for tuning in.